Okay, let's get us started. Uh, so we'll be focusing on questions that are relevant for week 3. And okay, let me just take it down. Okay, so we'll be covering questions which are relevant for the week 3 of this course. So first question is that you're given a okay, so you're given a simple perceptron f such that from R4 to R, which uses the 10 hyperbolic function as its activation function. The input vector is given here, and the corresponding weight vector is also given. Compute the derivative of 10 hyperbolic x at this. Acha, okay, so we have to calculate the derivative of 10 hyperbolic z, where z is the linear combination of the weight vector w and input vector x. So first of all, is it audible? Is it audible? Can just acha, not presented as well. Okay. Hmm. Okay. Okay. And visible as well, no? Hmm. Okay. So continue. So repeating again. So a perceptron function f is there, and which uses tan hyperbolic function as its activation function. Okay. You give an input vector x, w vector, weight vector this. Derivative of tan hyperbolic z is to be found, where z is the linear combination of w and input vector x. And ignore the bias term. Okay. So there are no bias term. So so this is how we have to handle it actually. So z is equals to w cross x dot w dot x means w multiplied x. Okay. Or dot product. Okay. Just linear combination. Very easy to understand. And now the derivative of this. So let me just show you in detail. I think I had done this in previous class as well. So taking derivative of it is like divide rule. Okay. So derivative of this, okay, and multiplied, this becomes square, okay, plus, not plus. So using the divide rule, Okay, so this becomes 1 minus, as you can see, 10 hyperbolic h square of this. Okay, this is our answer, as you can see. And now z is given here. Okay, and you have to find this value. Okay, so just show you 0.5 into 0.6 is 0.3. Okay, 1.5 into point 0.7 is 0.105, right? Yeah, 1.05. Okay, so this will be 1.05. Next, minus 3.6, minus 0.36. So 1.05 minus 0.36. And then 0.24. Okay, now this becomes, uh, so as you can see, this is 1 and minus 1.41 and plus 0.54. Okay, and so this becomes 7, and this becomes this one, minus 0.87. Okay, and now just putting this value, so 1 minus this. Okay, so you have to get this one. Okay, you should use a calculator for this, and you will get the answer for this question. Okay, any doubt? Okay, moving on. So next question is on dropouts. Okay, so dropouts is one technique developed by Geoffrey Hinton for for having robust neural network training. Okay, and so to understand this question, first let's look at the dropout paper. Okay, so as you can see, um, so what happens in dropout is that, so you have a neural network model. Okay, and like this, and these are the connections like this. And so what happens during training, what happens without dropout, this perceptron, okay, or this nodes, what happens that they specialize in some sort of task, okay, but they completely fail at other. What that means is that that leads to a uh, leads to not robust training. Okay. Now what happens that if you drop one of the nodes during training with the probability suppose p, then every node is forced to learn a most of the learning that is required. They have to learn all of that themselves, because what happens that you cannot rely on one node to learn it all. Okay, so that sharing of learning is important. So this is the reason that dropout leads to a robust learning in case of neural network. Okay. So if you check out the paper, uh, so the overfitting is greatly reduced by randomly omitting half of the feature detectors on each training case. This helps prevent complex co-adaptation in which feature data. Random dropout gives big improvement on many benchmark tasks, and as you can see, so there you can see another overfitting can be reduced by using dropout to prevent complex co-adaptation on the training data. On each presentation of each training case, each hidden unit is randomly omitted from the train network with the probability 0.5. So they omit with the probability 0.5. Okay, I mean which node will be omitted? It is during training. It is with 0.5. So a hidden unit cannot rely on other hidden unit being present. This is the important thing. So a hidden unit cannot rely on another hidden unit being present. Okay. So you can stop me if you don't understand. Okay. Uh, okay. Not going too much mathematical on this. Okay. Just understanding the basics. So what happens, to summarize what happens in dropout is that so during training with some probability one of a few of the nodes will be dropped out at each iteration, which leads to the nodes being independent of each other, and are forced to the uh, learn the representation that is required, and they cannot depend on other nodes because they may not be present during training. So that is what is done. Okay, so dropout happens with the probability p. Okay, so it remains with probability 1 minus p. Okay, during test time what happens is that each of the output of the node is adapted with 1 minus p probability, because that is the probability of being remaining in the network. Okay, so that is done. Okay, another way to view the dropout procedure is that very efficient way of performing model averaging with neural networks. So it is called like model averaging with neural network. A good way to reduce the error on the test set is to average the prediction produced by a large number of different networks. So it is like averaging output produced by a large number of neural network. Okay, so it is like that ensemble ML methods, if you know, uh, bagging, boosting, somewhat like that in this respect. Okay, so what we are doing is that ensemble of. So what happens that suppose you remove this node. Okay, next case you next iteration you remove this node, next iteration you remove this node. So what happens that it is like the data is getting trained on different networks, and then finally during test time you are interpreting the network. Okay, so that is what you're doing. Okay, so it is like model averaging. The standard way to do this is to train many separate networks and apply each of these networks to the test data, but this is computationally expensive during both training and testing. So random data is also computationally efficient. We use the standard stochastic gradient descent procedure for training the dropout. So we are using stochastic gradient methodology. So the training time we have understood, okay? So you're following, right? What I'm saying. So you're the two important things that we have covered is that what is dropout. So it means that with the probability P, one of the nodes is dropped from the network, and and it can be seen as a model averaging during training. So you're training on several models and then averaging the output. Okay, averaging uh, into a new model. Okay, so like that. Uh, so and also this is done in a computationally efficient way. Okay, that is what the author says here. And next, what we have is a so next that was in the training time. So next, we're looking at the test time. So test time, we use the mean network, so the model average network, but with their outgoing weights half to compensate for the fact that twice as many of them are active. Okay, so what happens that with zero point 0.5 it was dropped. Now during test time, what they are doing is that they halve the model weights. Okay, weight of every connection. Okay, because twice of them are possible because they were training with zero point 0.5 of dropout during test time, as every one of them are remaining, so they halve the weight of each connection. Okay, in practice, this gives very similar performance to averaging over a large number of dropout networks. In networks with single hidden layer of n units and a softmax output layer for computing the probabilities of the class labels. Okay, so this is what is dropout is about. Okay. Next, let's look at the question. So, dropout during training causes the network to overfit because it randomly dropped neurons, making the model too simple. So, that's wrong actually. So, dropouts does not lead to overfitting, okay, because we're also averaging during after each of the models, okay, uh, after it has been trained in one iteration, okay. So, the overfitting does not happen. During training with dropout, the network adjusts the activation levels so as the output remain consistent when dropout is not applied during inference. So, so that is wrong, right? So what I think they mean here is that to have a smoother training, that is what they're doing. Okay, so that way it is correct. Okay. Dropout in training leads to smaller final model size, fewer parameters, as some connections are permanently removed. So that is wrong. No, none of the connections are permanently removed. They are removed with a probability p. The final output during training when dropout is applied is multiplied by the dropout rate to maintain the expected output when. Acha. So that is not done. Okay. Okay, moving on to this question. So what you are having is that, so these are the regularization is given. L1 regularization, L2 regularization, and and this is batch normalization. Okay, so this is L1 regularization, L2 regularization is there. Okay, so uh, so to show what is L1 L2 regularization, okay, let me write it down. That's better. So in L1 regularization, what you're doing is that you're given this L loss function, theta, okay? Theta is a parameter here, okay? And so suppose any loss is there, okay? Uh, so what you do is that in when it comes to neural network, for each layer, in suppose in layer you have k nodes, okay? So I equals to 1 to k, and for every layer j equals to 1 to n, what we do is that we attach this theta ij parameter, and L1 loss, L1 regularization, we take the mod of this, okay? In case of L2 regularization, j is equals to 1 to n, and here I equals to 1 to k. In case of L2 regularization, we do this, okay? Now, so this is L1 L2 regularization first of all, okay? There are several features of L1 L2 regularization as well, which I will discuss right now. Hmm? Then we'll move to batch normalization. Now in L1 regularization, which is this one, so what happens is that induces sparsity. So what it means is that, so first in any regularization, what happens is that, so using so you're attaching acha. So here also there is a lambda factor which is like determines how much regularization you want, okay? And to normalize that, divided by n and k, okay, so that it does not blow up during training, okay? So here, so here what you have is so here what you have is when you are using any regularization, what happens is that it is attaching a theta term, and theta term is also there here. Suppose theta ij, a specific I and j is also here in the loss function. Suppose squared error loss function or anything, okay? But you're also attaching another term, and the amount, the magnitude of the term is controlled by this lambda. So what happens is that the terms here in the actual loss is reduced, okay, in both of these, okay? In case of this L1 norm, what happens is that it is reduced to a greater amount because it is the feature of this L1 norm. So what it means is that, so we are so what happens is that the 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 loss that we have here is the likelihood, it comes from the likelihood term that during uh, what do you call that? Maximum likelihood estimation. Okay, and this comes from the prior term. Okay, these two. So for this L1 norm, uh, what we use is a uh, Laplacian prior. Okay, and for this L2 norm, we're using a Gaussian prior. So the Laplacian prior is always induces sparsity in a model. Okay, and Gaussian prior, what happens is it regularizes to a smaller extent. Okay, and but if you need less number of parameters in the model, this is the way to L1 norm. And if you just want to reduce the parameters little bit, then this is the way to do it. Okay, L2 norm. Okay, and okay, so now we have to move to batch normalization. Okay, so let's do that. With batch normalization, accelerating deep network training by reducing internal covariate shift. So, so what we observed is that uh, so what we observed that so for better performance, what researcher used to do is that they used to increase the number of layers here. So they used to increase the number of layers to get a bigger model, which will learn better. So what happened was that after 6 to 7 layers, if we increase the number of layers, what happened that the test accuracy wasn't improving, but more importantly, even the training accuracy wasn't improving. Okay, when actually training accuracy was going down, the training accuracy was reducing more. So it was 8, 9, and 10. As you increase the number of layers, then accuracy goes down. So what happens? The situation was not of overfitting or something like that. So it was something else. What happens is even during the training time, it wasn't able to learn. Okay, the accuracy was low. So to understand this paper, actually, this phenomenon, this paper was written, and they devised batch normalization as one solution to address this problem. So, so what we're doing is that first to understand the problem, okay, what is there. So deep learning has dramatically and advanced the state of the art in vision, speech, and other areas. Stochastic gradient descent proved to be effective way of training the. This is the optimizer, okay. Stochastic gradient descent. So with momentum, these are the ADA-grad, RMS prop. These are the optimizers are there. So you need to optimize this. Okay, this is the loss function you have here. Lx theta summation over all these samples. Okay, you're taking and argmin over theta when where x1 to n is the training data set. With SGT, the training proceeds in steps, and each step we consider mini batch x1m of size n. So this is the classic way. There's nothing much here. Oh shit. So sorry. So I got this one wrong actually. I just confused it with uh skip connection in the resonate paper actually. Oh sorry. So this is batch normalization. This is not related to it actually. I gave a wrong pretext. Sorry. So So, so that was not the problem, batch normalization. So with many batch they are doing it, okay? So, so in normalization, what you used to do, to normalize the data, okay? At so what we are feeding to this is normalized. That is easy to do. But what happens is that the data that goes here, this layer or this layer, is unnormalized. So normalization of subsequent data traveling, means the information that flows through layers, okay, and normalizing them, okay, is called batch normalization. So in batch normalization, the batch size is important, of course, okay, and so that is it. And so let me explain this. First, let's understand the internal covariate shift, okay. So the changes in the distribution of layers input presents a problem because the layer needs to continuously adapt to new distribution, okay. So what happens, the distribution is changing, okay. So when the input distribution to a learning system changes, it is said to experience covariate shift. This is typically handled via domain adaptation. However, the notion of covariate shift can be extended beyond learning system as a whole to apply to its parts such as subnetwork or layer. So what happens is that the distributional shift is called the covariate shift. Okay, that is what they explain. But the covariate shift can happen to each layer as well, as I explained, not just to the input data. Okay, so consider the layer is there. Okay, so this is what you have here. So to deal with layer-based covariate shift, we introduce a new method called batch normalization. So that is how they explain it. So the formula for the batch normalization is this: for a kth batch, okay, k is the batch here. Okay, so that is what they have shown here. So first, so this is normalized x in a batch, okay. So what they're doing, they're subtracting the expectation over the batch and then dividing by the variance, okay. So it can be practically, it can be more challenging because this computationally means mathematical problem happens when you write code. What happens that if the numbers get too small or too large, that problem happens. So you have to apply a this epsilon, very small value, for numerical stability. So they do that, and then you can get to this batch normalization. Okay. Hmm. This is what we have, batch normalization. This is our question here. So batch normalization cannot be used together with L1 L2 regularization. So that's wrong. It can be used, okay, and there's nothing to stop. Regularization is just the parameters does not get too big, and it does not lead to overfitting, okay. And batch normalization is for this is robust learning, okay. L1 regularization can lead to sparse weight matrices. That is correct. Batch normalizes the input of each layer by subtracting the batch mean and dividing with the batch standard deviation. Slows down the training. So it does not slow down training. Using batch normalization is to disable during inference. Hmm. So B and D. Okay, like that. So let us take a short break of 5 minutes. Then I will come back. Okay. Okay, so RMS prop algorithm for optimization of a neural network, of optimization of the parameters of a neural network. Okay, so let's check that out. Okay, so for that I have opened this one. Okay, so just to get to where we are, so we used to have gradient descent for optimizing convex function. Now we move to SGD, stochastic gradient descent, because the number of parameters, not parameters, the number of what do you call that? Number of samples in a neural network is huge. Okay, a neural network training is huge usually. Okay, so you take batch of it. Okay, so stochastic or batch gradient descent. Okay, so next what you have, you introduce. So now what happened, that stochastic gradient descent did not work too well as well, because what happens that the neural deep networks, uh, I mean the loss function is not convex, and it can usually stuck in the uh, local minima. Okay, so what happened, that you use the concept of momentum. Okay, so momentum, and so these things were there. So Nestorov momentum algorithm came. Next, you have this ADAGRAD. Okay, so in ADAGRAD, you can say that we are using a moving average, okay, of different quantities, and then finally RMS prop algorithm, in which you have the training set and the corresponding y targets. So this gradient, compute the gradient G here, and then we're accumulating a moving average of the gradient. Okay, with the rho there, rho is something here, decay rate. Okay, so this is the decay rate. Okay, R is the initial accumulation variable. Okay, so you're accumulating the gradient and then finally calculating the parameter update. Okay, uh, so that is it. Okay, now finally applying this update. Now you're having this problem, so you need to find the value of theta t plus 1. Old theta t is given as 1.8. Aggregated gradient is delta theta t equals to 0.6. Gradient accumulation r t minus 1 equals to 0.4. Learning rate is equals to 0.1. Decay rate rho is equals to 0.6. Small constant del is given. Okay, so what you have to do is look at this formula, and so what you have to do is theta. Okay, so parameter update is required. Theta Okay, so what we have to do first, write theta t, that is 1.8. Okay, del theta is minus epsilon over, as you can see. So the learning rate epsilon here, okay, and so minus learning rate is 0.1 under root r is 0.4. The small, that is not required here, okay, because 0.4 will be able to handle it, okay. Into product with g is the accumulated gradient, okay. R is this one. Sure. So what I've done, RT minus 1 is given. Okay, R at previous step is given. You have to calculate R at this step, okay. So that will be this rho is given 0.6 into 0.4 into 1 minus rho is not into plus 1 minus rho is 0.4 into g dot g, okay, and the gradient we have here is mm, actually aggregated gradient is already there, huh? That is g, huh? Okay, okay. So g dot g aggregated gradient is this one, 0.36, ठीक है sir, 0.24 plus this 54.144. Okay, how much this becomes? 448, and this is 0.384. Okay, so this is 0.384. Okay, next what we have here is multiplied g, that is 0.6 here, 0.384, 0.6. Okay, this is the one. Okay, and let's use the calculator here. 1.8 minus 0.1 divided by 0.384 to the power zero point 0.5, okay, into 0.6. Set. So 1.703. Okay, next what we have is question number 5. So consider neural network being trained using different type of gradient descent method. The batch gradient descent leads to memory inefficiency during large data sets. Okay. So as you can understand, if the batch size grows, the gradient descent will have the same problem of gradient descent. Stochastic gradient descent have a noisy path because you're only taking one sample at a time. Okay, so the stochasticity is there. Many batch gradient descent is always faster in terms of computation time per epoch compared to batch gradient descent. That's correct. That's not correct. Huh? So always, okay, may not be always. Stochastic gradient descent guarantees faster convergence to the global minimum. This uses the variance of the, okay, this is it. Okay, next question is this. Mm, so the solution is here. Okay, so what you have to do is this one. Okay, so you can calculate. Okay, this is it. Any doubt? No doubt, right? So we'll be finishing off here. Okay, so we'll be finishing off here. Okay, any doubt? Okay.